Basically, it's functions cut into pieces. So before we actually do any, I wanted to show you guys this cool math website because math is cool, right? But it actually has a really good just description of how they work in general. So we're going to just use this as an overview to look at what a piecewise function is, what kind of notation you're going to see, and what it means, and then we'll go through our own separate examples. So this just to give you an idea overall of what's happening. So first, notice that a piecewise function has pieces to it, right? It's not just y equals one certain equation. Here there's two, and there could actually be as many as you wanted. Okay, so there could be like a list of 10 equations if they wanted to include them. Okay, and then notice that after the equation comes something that looks like how we write our domain, right? And what it's saying is you're only going to use this function in this part of the domain. Then this function is going to get like cut off. And in the next part of the domain, you're going to be graphing this next function. Okay? So you see in the picture below that they say it's basically like a fence. The reason they said their fence, so to speak, is at 1 is because notice 1 is the number where the x values change. If x is less than 1, you're using one of the equations. But if you're plugging in x values bigger than or equal to 1, you're using a different equation. So it's like over here, you're going to be graphing something like you normally would, and then once you hit the fence, all of a sudden you're going to change gears, you're going to stop graphing that equation, and on the same graph, you're going to start graphing this new equation. Okay? So the graphs look funny because they look like one shape, and then all of a sudden they change shapes, and then all of a sudden they might change shapes again, depending on how many equations and how many fences or changes in domain that you have across the way. Megan? Uh-huh. It's not in. Yes. Okay. All right. So notice that each function ends up in a certain area of our graph. So they put the green function over here on the left side because it said that it's supposed to be when x is less than 1. So not only is 1 the boundary, but the function that's next to x is less than 1 is going to be on the less than 1 side. And the function where x is greater than or equal to 1 is going to be on the greater than or equal to 1 side. Okay? So then it says, figure out who's the fence owner or who lives on the fence. Okay? And then notice it points out this one right here. Why is it choosing that second part of the equation as what lives on the fence? Shelby? Good. So it's just like when you're graphing inequalities on a number line. You know, if it just said less than, you put your endpoint as an open endpoint. But if it said less than or equal to, you would bubble in the endpoint and close it and show that it could go all the way up to that point. That's the same thing you want to do here. This first equation said only when x is less than 1. So here's a graph of that first equation. All this stuff is fine because it's less than 1. And then open circle right at 1 because you want it to go right up to 1, but you can't actually include 1. But 1 will be included on the second graph, so you'll see a closed-in endpoint for the second part of the graph. So notice that the first one looks like a line. That's because its equation was linear. The second one looks like part of a parabola, and that's because it was a quadratic. Okay? But they just started the parabola at the point they were allowed to start it with. It's filled in because it kind of owned the fence, or it was equal to. Okay? And then the graph just continues from that side. It's not always, they don't always make it so that it's the vertex of your parabola where you are. It's nice when they do. But they could have maybe continued this to 2, like they could have made 2 where the fence is, and then it would have just started here, but it wouldn't necessarily be the vertex of the parabola. Okay? All right, and so this is what the ending graph looks like, and this line doesn't actually exist. Okay? The fence is kind of like just for our own mental understanding of what's happening on the graph. So really, when someone looked at the graph, think how weird it would look to them. They'd see like, oh, there's a line. Oh, wait a minute. No, there's not. There's a parabola, and it like jumps down here to continue. And if there was even a third piece, it would look even more odd, right? Because this parabola would get cut off somewhere else, and then there might be another shape, and it might connect to it if they share an endpoint, or it might do what these do. It might jump apart and then start its graph somewhere else. Serena? No. This one's going to keep going in that direction, but it was only allowed to start from here, so it doesn't. They might. So if this equation was a little bit different, or if they shifted this parabola up 3, like if they had a plus 3 at the end, right, then it would have started right here at this endpoint and went like that, and that can happen too. Okay? Just depends on the endpoints in the equations. Maddie? So the open circle is that not both equations occur when they're equal to 1. So this equation, if we go back to the very beginning, it said that that equation was only when it was less than 1. And the other equation was when it was less than or equal to 1. So see right here in the very beginning of this domain, this is not actually allowed to include the number 1. So it can't have a filled-in point when x is equal to 1. But this one can because it can actually be equal to 1. Oh, like how did it know that it should end at 3? Okay, so that's where our graphing skills are going to come in. How did we know to get this line here? Well, we're going to graph this line however we know how. So we could put the y-intercept at 2 and go up 1 over 1 or down 1 over 1 and then just draw the line, making sure we continue in the area we know it's allowed to continue, and we cut it off at the point that we know it should cut off. And the way I would know this is exactly 3 when it's at 1 is I could actually plug the 1 value in here, right, for x, and see that 1 plus 2 is going to give me 3. And that's where that point will be. Okay, so we're going to have to plug those x values in to our equations to see those endpoints, and we're going to graph the equation how we would normally graph it, being aware of the shapes we expect. Okay? Does that make sense for kind of like an overview of what we're doing? Yeah? All right, so let's actually try some. Before we graph, I just want to make sure you guys understand the domain notation. So there's a function that we're going to actually graph a little bit later in class, okay, up at the top. So that's one function, but it's a piecewise function because notice it's cut in pieces. There are 3 pieces, right? One thing we graph when x is less than 0. One thing that we graph when x is greater than or equal to 0 but less than 4. And one thing we graph when x is greater than or equal to 4. Okay? So picture for a minute the fences like you guys just saw on the other graph. Where would we have fences for this equation? Where are we changing from one part of the graph to another part of the graph? So 0 is where one fence would be, because notice the first one only happens less than 0. And then if you want to be bigger than 0, you have to go to the second function. Okay? Would 0 be the only fence for our equation? Also 4, right? Because then the middle one we can graph all the way till we get to 4, but at 4 it switches to another one, so there would be kind of another barrier. And again, those barriers don't actually go on your graph, but they're good images for us to understand we're kind of cutting the graph off at those points. You guys can put a line there and then just erase it when you're done. Okay? All right, so the reason I point that out, though, is if someone asks you to find f of negative 3, f of 5, and f of 2, we understand that that means you plug those numbers into the f function. But now the f function is no longer simple. It's not one equation. It actually has 3 parts to it. So you have to know which part do you plug into. So if I'm trying to find f of negative 3, where am I plugging negative 3 into? Do I plug it into all of them and get 3 different answers, or just pick the one I think is best? Do I plug it into one specific one? If so, how do I know which one? Jordan? Good. Okay. This is an x value, and we have to abide by the rules they set for the x values or for the domain of the function. Negative 3 is less than 0, so you can only plug it into the first function because that's where you plug in x values that are less than 0. Okay? So f of negative 3 is only one answer, and it's the answer I get by plugging negative 3 into the first branch of that function, which would give me 9. Okay? All right, somebody else, what about f of 5? What would we do to find f of 5? Matt's talking to me. I see Jordan's hand. Caitlin. Good. So we're going to plug it into the third portion of the function, because when we look at the x values, that's for when x values are greater than or equal to 4, and 5 is greater than or equal to 4. So we're going to plug 5 into the third portion. So that would give us 7. All right, and then how would we find f of 2? The second one, because 2 is a number that falls between 0 and 4. And the second equation has the domain attached to it that says x values between 0 and 4. So 2 would get plugged into the square root. And you would either just leave it square root of 2, or if you want to, you could put it in the calculator and get 1 point something. Okay? Does that make sense, just so that we see the separate portions? All right, so now let's try to actually graph some of them. Okay, so the first one we're going to try to graph is f of x is equal to 3x plus 1 and also x squared minus 2. So it has these two pieces to it. Okay. And I'm going to go ahead and do what you guys are going to want to do, especially now at the beginning, like Matt asked. And I'm going to go ahead and draw the fence up on the board. So where should our fence or our changing of functions occur? 0. So when x is equal to 0. So here. So I expect to see one type of graph on the left side and another type of graph on the right side. Maybe their endpoints will meet on that boundary. Maybe they won't. Okay. What graph do I expect to see on the left side? The first one. Okay. So 3x plus 1. So I'm actually going to write that on the left side of my graph. It just helps me keep track. And then the x squared minus 2, that's going to go on the right side. For the 3x plus 1, when it reaches the boundary, is it going to have an open endpoint on the boundary or a closed endpoint on the boundary? Closed, because it can actually plug 0 in. So I'm actually going to go like this next to this to help me remember that. Okay. And then notice my second function is going to have an open endpoint on the boundary. So I'm just going to go like that. Okay. You don't have to do these things. These are organizational things to help me get through the problem. Taylor?
Why is it a closed circle?
So notice in the first one that the domain, we realize they're split at 0. One's for when it's less than 0, one's for when it's greater than 0. But which one are you allowed to use when you want to actually plug in 0? So if you wanted to plug in 0, you wanted x to be equal to 0. Which function allows x to be equal to 0? The first one, because of the equal to. That's why it gets the closed dot, because you're actually allowed to plug in 0 for that one. But for the other one, you're not technically allowed to plug in 0, but you want to show where it ends at the boundary. All right, and then just for some point of understanding, what shape do we expect on the left side? A line. And on the right side? Part of some parabola. Okay? And so you guys have a few ways that you could go through graphing these. Now, for lines, okay, normally you guys like to use like slope-intercept form. Okay? And you can either graph them right on the graph, or if you want, because sometimes the boundaries get a little bit difficult, you could put the graph off to the side and then just transfer the part of it you know belongs in the portion for your final graph. And what I mean by that is if I were to graph the entire graph of y equals 3x plus 1, I'd have my y-intercept at 1, and I would go up 3 over 1. Or I would go down 3 over negative 1. Whatever the case may be, this is the line that I would get. Okay? But I don't want that entire line on the graph, right? It's getting cut off right here, and I only want it on the left side of that boundary. So what I am going to put on my graph is this portion of it right here, the only part I'm allowed to put on, the stuff when x was less than or equal to 0. This is the part they're making me exclude. Okay? And at the boundary, it does get the full point. So now I'm going to go ahead and transfer this over just with the couple points I see. So I'm going to put that point at 0, 1. And then down 3 over 1. Or just see the point negative 1, negative 2. To help me draw the line that's going to go that way. Okay. So there's one piece of my piecewise function. Okay, so one piece is done. Jordan? Yeah. The quiz isn't on this. Okay. All right. So the second part of your function is a quadratic, and let's think about where this quadratic is if we were graphing the whole thing, and then we can cut off the piece that we need. And again, you don't have to do it this way. You can do it directly on there. But you guys are a lot better at graphing the whole thing, right, now that we've done stuff. So it seems like it'd be faster for you to do that and then just kind of think of where the boundary is than try to find a new method of graphing it. So if the equation is x squared minus 2, what transformations have been made from the parent function? Down 2, and that's it. Okay? So normally our vertex is at 0, 0. This vertex is going to be at 0, negative 2. And are we stretching or compressing it in any way? No. So it's going to follow the normal pattern, which is one space away goes 1 unit up. And then 2 spaces away horizontally goes 4 units up. And again, how I know that is that I memorized my parent function, or I could redraw it. So this is the graph of x squared minus 2. That's the entire graph of x squared minus 2. Okay? But I don't want the entire graph. Remember, I have a boundary right here. And I'm only supposed to use which part of this function? On the right side of the boundary or the left side of the boundary? The right side. So this part here. And am I supposed to have a filled-in endpoint? Am I allowed to equal 0 with this function? No. So the boundary point has to be open. Okay? So it's going to have an open boundary point at negative 2. Okay? And then I'm going to plot these other points that I now know are on the right side of that. So 1 over from that 1 up, and 2 over from that 4 up. Okay? So there's a graph of that piecewise function. So no new shapes, but having to understand this notation and then put this new graph together. Does that make sense? Okay, any questions about this one? Okay, so if you had to list the domain and the range of this graph, which is kind of weird, okay, because they split the domain into 2 parts, but once you're looking at the finished product, okay, if you had to list the domain, so think left and right, are there any restrictions on our domain? Now, we can plug things less than 0 in, and we'd end up on this line, right? Can we plug 0 itself in? Yeah, we'd end up right there. Can we plug in things that are greater than 0? Yeah, we'd end up somewhere on this parabola. Okay, and they continue. This one continues to the right forever, this one to the left forever, so there's no stopping point. So our domain is still all real numbers. It's weird because they don't all connect together, but you can still plug anything in. What about our range? Yeah, it is a little tricky. You do see that this is going up forever and this is going down forever. Yeah, okay, it seems like we're missing some stuff right here. But then, let's say I wanted negative 1 as a y value. This line has negative 1 as a y value somewhere on it, right? So even though there's this gap between the 2 functions, this part of the line right here still captures those y values below that. Okay? There's actually some points here where we have 2 places that capture the y values. Yes, not an asymptote or anything like that. It's just kind of a mental check for where my graph changed position. So our range would also be all real numbers because even though these graphs are separated, since they're not separated, so since they're separated but they overlap, they still capture all the values. Now, if your graph had looked like this, like they were spaced a little more apart, then you would have had all the y values up here and all the y values down here, but you would have been missing like this portion in the middle, and we would say that in our range. Okay? No. It was on 0 specifically because of the x is less than or equal to 0, x is greater than 0 given in the problem. Or then it would have been at 4. Okay? All right, any questions on this before we try another one? No? All right, let's try another one. And then your end result, like people were asking about kind of fence or the wall, that technically is not there. So like if you saw this graph in a book, you're not going to see that dotted line there. Okay? And the only reason I would ask you to erase it at the end is in the next section that we study, those dotted lines, like Matt was asking about, they actually mean some different things, and they do restrict things that we can plug in, and they become asymptotes, like you guys probably saw in Algebra 2. All right. So, how many fences? 2 fences? Just one fence, but kind of a weird situation happening here, right? Okay, our fence is going to be at 0, just like it was last time. What do you expect to see on the left side of the fence? The first equation. Okay. Megan? No. It will depend on the values. But see how right here they all changed based on 0? That's why there's only 1. So on the left side of the fence, we're going to see the absolute value equation. What do you expect to see on the right side of the fence? The last one, the x cubed. And at first, some of us thought 2 fences, right, because we saw the 3 equations. But this middle part is kind of unique. Jordan? So notice that it says, yeah. So they said, you're going to use absolute value. It's part of the problem. So they don't just give you an equation anymore. They give you an equation with where it can be used. So that first equation is only allowed to be used. They're relevant to the problem. Well, if they weren't, somebody came up, they're part of the problem, but if they weren't there, you wouldn't be able to graph the piecewise function because you would just have 3 entire graphs on the same thing. So x is less than 0, we're going to have absolute value. X is greater than 0, we're going to have x cubed. Okay? And then right here when x is equal to 0, so neither one of these have a closed endpoint. Both of them are going to have an open endpoint because neither one of those equations had x is equal to 0 included in it. But the middle one says when x is equal to 0, what are we supposed to get? 3. Okay, yeah, so that literally means we're going to just have the point 0, 3. Okay. Because I can't plug in anything else but 0, so it's only going to happen when x is 0. And there's not really anything for me to plug it into. It just comes out to be 3. Okay, so that's just going to be 1 point because it says just when x is equal to that specific value 0. All right, so again, we have to get the left side and the right side. So on the left side, our absolute value function, what does absolute value function look like? So I heard 2 answers. Okay, it looks like a V. And this one is the parent function. Okay, it hasn't been changed at all, so you should know. It has a vertex at 0, 0, points at 1, 1, 2, 2, okay, and it looks like this. And our cutoff is at 0, 0. And this function is only happening on the left side of the cutoff. So it's over here with an open endpoint. Okay? So open here. So it looks like a straight line because we cut off the other half of the absolute value. Our second function, or actually the third one in the list, the x cubed, okay, is also a parent function, no shifting, so that makes our life easier. So both our cube and our cube root function have 0, 0, 1, 1, and negative 1, negative 1. Mm-hmm. I'm showing you, so what I'm showing you is the whole graph of the function, and then I'm trying to say, okay, but what part am I going to put over here on my actual graph? So I'm saying, oh, the fence is right here, and this is only on this side of it. No, yeah, that's what I'm saying.
How do you know, like, how did you know?
So see how it said absolute value of x, what came after it said when x is less than 0? So on the x-axis, you're only allowed to graph that one using x is less than 0. So those are like directions of where to put the graph. Skylar? Leave one circle. Yeah. So this is the graph of the cubic function. And then again, like Matt was asking, all I'm doing over here is it's easier for me to graph these like this because we've done it so often, and then just kind of cut off the part I don't need. So I'm saying like, okay, this is where the cutoff is, and I want to use this side of the graph, and that needs to be open. So then I'm going to put those points over here. This is already there, like Skylar was pointing out, and then this is going to be curved steeply upward like that. All right, so what is the domain of this function? All real numbers. You can still plug in stuff less than 0, stuff more than 0, and exactly 0. What is the range of this function? So look at the y values. Well, so it put this point right here. So the funny thing is these things connect, but is the point 0, 0 really on our graph? No, it's like where both of them end, but they never touch 0. If you plug in 0, you actually get 3. It's like the single point that's been removed from the graph kind of looking thing. Okay? So what is our domain for this graph, or our range for this graph in this situation? Good, y is greater than 0. Okay, so there happens to be points in many places. It doesn't go below 0, and it doesn't include 0 because we don't actually hit that point. So y is just greater than 0. Okay? All right, let's do one more where we don't have everything happening at 0. So let me see which one's best. We'll do this. Okay. All right, so there is still some action at 0, right? See that the first function only happens when x is less than 0. But then the next one happens between 0 and 4. And then the next one happens when you plug in numbers more than 4. This is the one we first plugged into on the first page. And remember, if you were plugging in -3, you plugged it into one part. But if you were plugging in 5, you plugged it into a whole different part. Okay? All right, so where are my fences, so to speak? Good, 0 and 4, because we have a change in function at 0. 0 is a boundary for that one. Okay, and then the next one starts, but it ends at 4, and then 4 is the boundary for the next one. So we actually have two sections on our, or two fences on our graph, one at 0 and one at 4. So when x is smaller than 0, I have x squared. In between 0 and 4, I have the square root of x. And then when x is bigger than 4, I have 2x minus 3. Okay, so over here. So the first one is only going to have one endpoint because it's only going to hit one fence, right? It can keep going to the left as far as it wants, over here on the left side. But it's going to have an endpoint when it hits the fence. Is the endpoint going to be open or closed for the first one? So look at x squared. It says when x is less than 0. Is it equal to 0? No, just less than. So it's going to be open along that fence that it hits. Now the square root of x is going to hit two fences, okay? It has a starting fence and an ending fence. It's only contained in between the space of these two fences. So it's going to kind of have two endpoints, okay? One at 0 and one at 4, as you see in the inequality. What are the endpoints going to look like? Closed and then open. So closed at 0, open at 4. So I'm just going to kind of go like this. Those aren't where they belong, but that's just going to help me remember for later. Okay? I don't know. Let's see. All right. So then the next one has only one endpoint. It has this fence, and it can go forever to the right. And notice it's allowed to be equal to 4, so it's going to have a closed endpoint. So f of x equals x squared is the parent function that we should know. So 0, 0 is the vertex, 1 over 1 up, 2 over 4 up. Okay. So that parabola. Okay. Think about where your fence is cutting that off at 0. So you're only graphing this portion that's to the left. Okay. And we already decided the endpoint would be open at the wall that it hit. Okay. So an open endpoint at 0, 0, 1 over 1 up, 2 over 4 up. So there's that part of that parabola. Then, in between the fence, I have my square root of x. Again, that's just the parent function. No shifting has occurred. So I know it has a vertex at 0, 0. 1 away is 1 up, and 4 away is 2 up. And it looks like this. And it has two fences limiting it, one at the beginning, one at the end. So one's at 0, one's at 4, and I'm just graphing what's between the fences. So that's the only portion of the graph that I want to include on my final graph. Okay? And to remind myself, I marked the endpoints over here, that it's allowed to have a closed endpoint at 0 and an open endpoint at 4. Okay? So closed endpoint at 0. So this was Skylar's question. There's already an open endpoint there. But now so that before meant 0, 0. It's kind of what the graph goes up to, but 0, 0 is not included on our graph. But now is the point 0, 0 going to be included on our graph? Yeah, even though it came from another function, it's now included. Okay? 1, 1, and 4, 2. Okay? And then the last portion of our graph is a line. Okay? Oops. So when we graph our linear function 2x minus 3, okay, that means it has a y-intercept at -3 and a slope of 2. So up 2 over 1, up 2 over 1, etc. But the fence that's affecting this function, okay, it's only going to exist after 4. So I didn't even graph all the way to 4. So I'm going to continue to 4. And it's important that I kind of know what that point is at 4, because if I'm going to cut my graph off at 4, okay, I need to know where some points are that I can put on my final draft of my graph over there. So if I was kind of stuck and I really wanted to know just what is the point at 4, okay, what would I do? Plug 4 in for x in this equation to find out where this equation hits that boundary, okay? So if I plug in 4 for x in this case, or in other words, calculate f of 4, I get 8 minus 3, which gives me 5. So this is happening at the point 4, 5, okay? And it's going to be a closed endpoint. Jordan? Not in piecewise functions. There will be some other functions where we see actual asymptotes that will be horizontal. These are just kind of mental blocks, because at the end we'll remove them and we'll see what the graph will look like. So this graph's going to start at 4, 5, and then the line's going to continue after that. So I'm going to plot the point 4, 5, closed endpoint, because this function had a closed endpoint on that fence because of the equal to 4. And if I didn't have any other points, I can either get another point by plugging in another x value, or the fact this is linear and it has a slope of 2. Once you have your point, you can just go up 2 over 1, okay, and follow that pattern to see what your line would look like. So the actual graph of this function, you wouldn't see these little fences that we talked about here. You would just see this. Yeah, so it's kind of weird looking. What would be the domain of this graph? All real numbers. So I can plug in everything here. I have a point there. I can plug into the left. That looks empty, but then there's one right there, and I can keep going. So all real numbers. And the range